Hello dear all, this is Sadanand Malik welcomes you in entire physics, and today here we will study about Young's double slit experiment to study about the interference of light. Actually, Thomas Young performed the first experiment in the field of interference of light by using a combination of slits. Means here this experiment is based on the division of wavefront. Here the two monochromatic sources are produced by using the method of division of wavefront. So dear all, in this topic let us see which type of observations is found by Thomas Young and how we can explain these observations, means how we can explain the reason to find this observation here. So let us consider the experimental setup of Young's double slit experiment. So dear all, let us consider a slit. Suppose we have a point source of light. Suppose S is a point source of light. Okay, now obviously if it is point source of light then it will emits the light rays in all the possible directions. So suppose these are the movement of light rays in all the possible directions. Obviously here the light ray will move in form of waves. So here in form of waves. At the same instant which waves are formed, if we draw a tangent line or if we draw a tangent surface which is tangential to the tip of these waves, then we will find a wavefront. So by this way we have a wavefront also. Now suppose S dash is the source of light. Now in front of this S dash, suppose we have a slit S. Suppose we have a slit S. So suppose this is slit S. Now what will happen when this wavefront will incident on slit S? So suppose this wavefront is allowed to incident on slit S dash. So in this portion, due to the Huygens principle, wavelets are produced. That's why from here, from this transparent part, again the secondary wavefronts are produced. So suppose this is the secondary wavefront, here this is the secondary wavefront. So here beta, because we have to perform the calculation here, so let us try to draw the different wavefront corresponding to the crest and trough of the waves. So here let us show. So we know that beta, because a wave will move as in form of crest and trough. So suppose this is a wave. Suppose this is a wave. This is the crest and it is trough. Crest and trough. Again crest and then trough. Then the locus of all the crests of a wave is denoted by a smooth line. Here denoted by a smooth line, and the locus of trough are denoted by a green line. Denoted by a green line. Means here red line will give the locus of crest and green line will give the locus of trough. By using this concept, let us draw the diagram. So because this is a first wavefront, and again suppose this is the second wavefront, and again first wavefront, and then second wavefront, then first type, then second type. Now let us see how these wavefronts are drawn here. So dear all, let us consider the direction of wave. So in this figure, if a wave is moving along this direction, Then according to this figure, the locus of crest and trough will be cleared, as because red line gives the locus of crest. So here corresponding to red line we will have a crest, and corresponding to green line trough, then crest, then trough, then crest, then trough. By this way your wave will propagate through the media. Similarly, if we consider the other wave moving along this direction and another wave moving along this direction, so let us draw the waves corresponding to this wave front. Then we will have crest, trough, crest, trough, crest, trough. By this way the wave will propagate. Similarly, crest, trough, crest, trough, crest, trough, crest, trough. Means here suppose we have three waves. We are going to consider three waves: wave 1, wave 2 and wave 3, which are produced at the same instant t. Then the wave front corresponding to these waves are given by here this red and green lines. So here when this wave front will incident on a combination of slits, mean assembly of slit S1 and S2, suppose we have a combination of slit S1 and S2, such as suppose this is slit S1 and this is slit S2. Now slit S1 and S2 are situated such that S1 is equal to S2, means the separation of slit S from S1 and S2 are equal. Then what will happen when this wave front will incident on S1 and S2? Suppose like this, then what will happen? Let us see. Suppose this is the incident wave front. When will incident on the S1 and S2? Then obviously from here the Huygens principle, secondary wave fronts are formed. So here from S1, suppose this is a wave front corresponding to crest. From S2, this is a wave front corresponding to crest. Again, suppose this is the wave front corresponding to trough. Similarly, this is a wave front corresponding to trough, again corresponding to crest, corresponding to now corresponding to trough, by this way we will find the wave fronts. Let us draw some wave fronts, because here we have to find the observation. So more will be the number of wave fronts, observation will be clear. So here suppose the last one, let us draw the wave front for crest of waves, wave front for the crest of waves. So here from slit S1 and S2 we have two light sources having the same wavelength. Now if we consider a screen, in front of S1 and S2, suppose this is screen, then what will happen? Which observations we will find on the screen? Let us see. So from the mid of S1 and S2, let us start. From the mid of S1 and S2, let us start, means from this point we are going to start. So first point here, from the midpoint, the first point here, this is a first point. Obviously here both the red wavefront of S1 and red wavefront of S2 are intersects to one another. Means here the waves are in same phase. Again green and green intersects to one another. Again red, and then green and green. Means same colors of light intersect to one another along this line. So the light ray which will move along these points will give the maximum intensity spectral line at the screen. Suppose the point is given by O. O is a point of central point of the screen, and here the intensity is maximum. Again now let us move upward from this line or downward from this line. So first let us move upward from this line, then we will have the next point here. This is the next point, and corresponding to this point the green of S1 and the red of S2 will intersect. Again this is the next one, the red of S1 and the green of S2. Again the next point, the green of S1 and the red of S2. Again the next point, the red of S1 and the green of S2. And similarly by this way we have the points corresponds to the opposite phase interference. That's why whatever will be the light will move along this point will produce the minimum intensity on the screen. Means here we will find a dark fringe D1 suppose. Similarly, now let us move away from this line in upward direction. Then the next point here, this is a green of both, this is a red of both, green of both, red of both. By this way, corresponding to these points, means along these points, whatever is the light will move towards the screen will produce maximum intensity on the screen, and it will give the bright fringe, suppose B1. Similarly, let us consider the next point. Then the next point is this, the red of 1, green of S2, next green of S1, red of S2, green red. By this way we have many number of points. Corresponding to this point, if we draw a line, means along these points if we draw a line which will produce the minimum intensity on the screen, and suppose it is denoted by D2. By this way, as we move away from the D2 dash, means here from central point O, as we move away in upward direction, then we will have first dark fringe, then bright fringe, then dark fringe, then again bright fringe. So similarly in the downward direction also, let us consider the first point here. So here red green, red green, red green, red green, means corresponding to this point the light will have minimum intensity. So here D1 dash. Now again next point is red of both, green of both, red of both, green of both, red of both. Means along these points the line will produce maximum intensity here. So it is suppose B1 dash. Again the next point green red, green red, green red, green red. So this line will produce minimum intensity, means here D2 dash. By this way we will find on the screen as the central point. The central point is bright, having the most intense spectral line, and then dark, then bright, then dark, then bright. By this way we will find. Similarly central one is bright, then dark, then bright, then dark, then bright. By this way, means on the screen we will find the alternate bright and dark fringes. So this was the experimental setup of Thomas Young's double slit experiment. Observations which is found on the screen by Thomas Young. Thomas Young found following observations. First one is, on the screen alternate bright and dark fringes are found. on the screen alternate bright and dark fringes are found. Second one, the central fringe is most intense. Central fringe is most intense. Third, except the central fringe, all the bright fringes will have same intensity of light. Same intensity of light, and the dark fringes have zero intensity. This is the third one observation. Fourth one, the separation between two successive bright or two successive dark fringes are equal and known as fringe width. So these was the observations that is found by Thomas Young in their double slit experiment. Hello, now let us try to find the fringe width, means the separation between two successive bright and two successive dark fringes. To obtain fringe width, first of all we have to consider a experimental arrangement by this way. So here suppose we have a slit S. Suppose this is slit S, and this is the central line passed out through S, and in front of this slit S we have two slits. Suppose S1 and S2 are two slits, S1 and S2. Here the separation between SS1 and SS2 are equal. These separation are equal. In front of this S1 and S2 there is a screen. So there is a screen, and this is the central point of the screen, that is shown by O. Obviously in the observations we have seen that on the screen alternate bright and dark fringes are found. It means that if we consider a position, a point anywhere on the screen, suppose this is a point P considered on the screen having a distance y from the central point, then obviously at point P either we will find a bright fringe or a dark fringe. It depends on the path difference between the waves which are reaches from S1 to P and S2 to P. Means the path difference between S1P and S2P will give the nature of fringe formed at point P. So suppose the separation between S1 and S2 is, suppose the separation between S1 and S2 is 2D, and the separation between the assembly of slit and the screen is capital D. and the light used having the wavelength lambda, then we can find by using the Pythagoras theorem. So let us draw two lines, and here angle 90. Again draw lines, here angle 90, because we have to find we have to find S1, we have to find S2p minus S1p, because from figure S2p is more than S1p. So the path difference will be path difference delta will be equals to S2p minus S1p. We have to find this value. Suppose equation number 1. So dear all, if we want to find S1p and S2p, then obviously from this figure we can find it by using the Pythagoras theorem. So first of all, let us try to find S2p. So from figure S2p is equal to, from figure dear all, S2p may be written as, suppose this is M, suppose this is N. Then S2p will be equal to under root of S2m plus this square. Means here Pm, means here S2p may be written as, S2p is equals to under root of S2m whole square plus Pm whole square is equal to under root of S2m means d square plus Pm means y plus this distance, and this distance is equal to small d. This distance is equals to small d. So here Pm square is equals to y plus d whole square. Now it can be written as is equals to d square plus y plus d whole square, and the total power is half. So this is S2p. Similarly, suppose equation number 2. Similarly, S1p is equal to, from figure S1p is equals to under root of S1n whole square and Pn whole square. So we can write S1n whole square plus Pn whole square. S1n means capital D square plus Pn square means this separation. So it is y minus d. So y minus d will be equal to y minus d whole square. Here we can convert this under root as power 1 by 2. So d square plus y minus d whole square, and their power is 1 by 2. Equation number 3. So from equation 2 we have S2p, and from equation 3 we have S1p. Let us substitute these values in equation number 1. Then path difference will be, now the path difference will be delta equals to S2p minus S1p is equal to, S2p means d square y plus d whole square, d square plus y plus d whole square, and the power is 1 by 2 minus S1p as in equation 3 d square plus y minus d whole square power 1 by 2. Let us solve it. Then is equal to, let us take d square as common. Then we have from first term d square, when we'll take common then it will become d under construct 1 plus y plus d whole square upon d square power 1 by 2. minus, from here d square is taken common, so it will become d outside the bracket, and here 1 plus y minus d whole square upon d square power 1 by 2. Now by using binomial theorem, we have 1 plus x raised to power n is equals to 1 plus nx plus n minus 1 x square upon factorial 2 plus like this. So on applying this formula in our case, in this case, so here we have x is equal to y plus d upon capital D whole square, and n is equals to 1 by 2. So let us apply this formula here. Then delta is equals to d under koshtak 1 plus n. N means 1 by 2, x means y plus d whole square upon capital D square, because here y plus d upon d square upon d square is small enough. Y plus d is the separation between fringes, and capital D square is the separation between the slits and screen, as we can see in the figure. So here, because since y plus minus d is very much less than capital D, so here the higher order terms related to x square, related to x may be neglected here. So only up to second term we have to use the binomial expansion. So here this will be the formula, plus for the second term again applying the binomial theorem, then we have d under koshtak 1 plus n means 1 by 2, x means y minus d whole square upon capital D square. Now delta is equal to here again multiplying this d inside the bracket, then we have under koshtak d plus y plus d whole square upon 2d plus d plus y minus small d whole square upon 2d. So when we remove this bracket, then d and d will be cancelled out. 2d is common to both, so 2d will be as it is. Y plus d whole square may be written as y square plus d square plus 2yd. Similarly, plus, actually here it is minus, this sign is negative, so here it will be negative, y square plus d square minus 2yd. So y square d square will be cancelled out, and here 2yd minus plus 2yd means 4yd upon 2 capital D. On solving 2yd upon capital D. So here delta is equal to 2yd upon capital D. So this is the path difference, equation number 4. This is the path difference between S2P and S1P. And now as we know, hello dear all, now equation 4 gives the path difference ray S1P and S2P, because in our figure the nature of the fringe at point P depends on the path difference between the waves reaches from S1 and from S2. Now, as we have seen in the interference topic, if the path difference is integer multiple of lambda, then the intensity is maximum, means bright fringe. So here let us apply those conditions. Actually, we know first, for bright fringe, means maximum intensity. The path difference delta should be equals to integer multiple of lambda. It means that here equation 4, 2y d upon capital D should be equals to n lambda, implies then, because here capital D, small d and 2 are constant, so let us transfer them to the right hand side. Then we have y is equal to n lambda capital D upon 2 into small d. So here implies then y is equals to, now because lambda d upon 2d is constant, so here n lambda capital D upon 2 small d. So because here n varies from 1, 2, 3, etc. So here yn means this is the position of nth bright fringe. Suppose equation number 5. Now if we want to find the separation between two successive bright fringe, means let us consider two successive bright fringe. Suppose nth and n plus 1th. Then we have the position of nth fringe is given by equation number 5, and the position of n plus 1th fringe will be given as yn plus 1 is equal to, in place of n we have to substitute n plus 1, and the remaining terms are constant, lambda d upon 2 small d. And the position of nth fringe yn is equals to n lambda capital D upon 2 small d. Now here the fringe width. Now the fringe width will be beta is equals to yn plus 1 minus yn. Now let us substitute the value. Then lambda d upon 2d is common, so take it common. Lambda capital D upon 2 small d, under kostak we have n plus 1 minus n and n will be cancelled out, so here beta is equal to lambda capital D upon 2 small d. So this is the fringe width for bright fringe. Equation number 6. This is fringe width for two successive bright fringes. Now similarly, case second, let us consider dark fringe. For dark fringe, we know the path difference delta should be equals to 2n plus 1 lambda by 2, means odd multiple of lambda by 2. So here for dark fringe, the path difference we know is equals to 2n plus 1 lambda by 2. Obviously it means that our path difference which we have found by derivation is 2yd upon capital D is equals to 2n plus 1 lambda by 2. Now here, because D, 2 and capital D are constant, so here y is equal to, we can write 2n plus 1 lambda upon 2 into capital D upon 2 into small d is equal to, let us solve. So here we have 2n plus 1 lambda capital D upon 4d. So here, because it is n for nth dark fringe, so here write n. Suppose equation number 7. Now let us consider two successive dark fringes. Suppose nth and n plus 1th. Then yn is equal to, dash denotes here, this dash denotes here dark fringe. So yn dash is equals to, in place of n it will be n, means 2n plus 1 lambda capital D upon 4d, and yn plus 1 dash means n plus 1th fringe. It will become, in place of n we have to write n plus 1. So here 2n plus 1 into lambda capital D upon 4 small d. Therefore fringe width beta is equal to yn plus 1 dash minus yn dash. So it will become beta is equal to, because lambda d upon 4d is common, so lambda capital D upon 4 small d is taken common. It will become 2n plus 3 minus 2n plus 1. So on solving we have lambda capital D upon 4d under construct 2 and 2n will be cancelled out. 3 minus 1 is equals to 2. So here beta is equals to lambda capital D upon 2d. So beta is equals to this. Suppose equation number 8th. So from equation 6, beta is equals to lambda d upon 2d for bright fringes, and from equation 8, beta equals to lambda d upon 2d for dark fringes, which are exactly equal. From equation 6 and 8, fringe width are equal for bright and dark fringes, and here this is the condition of fringe width.